coronavirus has multiple parts. Inside the virus lies the genetic encoding that allows the virus to hijack human cells and turn them into virus factories. A protein encapsulates the genetic material known as the viral envelope. On the surface of the viron are S and HE proteins. The structure of the 2019 novel coronavirus is a mutation. For more information on this, see the link below. The large S glycoproteins are used by the virus to gain entry to human cells. They most likely attach to angiotensin-converting enzyme 2 receptors on the cell membrane, allowing the virus entry. The exact mechanism for this is not known, most likely as shown here.
Bioavailability. If a tablet releases the drug quickly, blood levels may become too high, whereas slow release may result in low levels of absorption. Additional factors affecting absorption and bioavailability include the properties of the drug and the physiology of the person, such as pH levels in the stomach and its speed of specific foods and other drugs can increase or decrease the speed at which drugs are broken down and thus determine their levels within the blood. A drug may be broken down to stop it from working. However, there are other drugs that need to be broken down or modified before they become active. These are known as prodrugs. Some drugs are directly eliminated.
If the immune system is not controlled, the effector T cells attack any unknown organism they find in the body. So if a virus enters the body, the T cells would be alerted to its presence by dendritic cells. Different T cells from those attacking the kidney will attack and destroy the virus-infected cells. The current protocol to control the immune system during a transplant is the use of immunosuppressive drugs. These drugs suppress the immune system, paralyzing it from attacking the transplant. At first, the T cells detect the foreign organ and still try to attack it, but the immunosuppressive drugs prevent this from happening before any significant damage has been done. However, here lies the problem. The whole immune system is paralyzed by the immunosuppressive drugs, so if a
slows the movement of your cilia, causing some of the smoke and mucus to stay in your lungs. While you are sleeping, some of the cilia recover and start pushing more pollutants and mucus out of your lungs. When you wake up, your body attempts to expel this material by coughing repeatedly, a condition known as smoke. Protein-building parts of your cell. Ribosomes use information from the genetic material to make other viral proteins, such as the H and N spikes. A packaging structure in your cell called the
inflammatory mediators such as interleukin-1 or IL-1, which activate dendritic cells, and chemokines, which recruit neutrophils, macrophages, and T cells. Activated dendritic cells migrate to the lymph nodes, where they present antigen from the site of infection to naive T cells, priming them to activate and differentiate into effector T cells. Activated T cells return to the skin and kill infected keratinocytes to control virus. Models propose that stressed keratinocytes might release self-DNA, which in complex with an antimicrobial peptide activates dermal plasmacytoid dendritic cells to secrete high amounts of the antiviral mediator interferon. Together with pro-inflammatory IL-1 alpha released by stressed keratinocytes, interferon activates dermal dendritic cells to promote T cell differentiation. The earliest recognizable change in the affected skin is the accumulation of T cells and dendritic cells around blood vessels in the dermis. An overt lesion occurs when CD8 T cells, dendritic cells, and neutrophils
Part of the innate immune system, called dendritic cells, carry information from the kidney to the local white nodes called lymph nodes through blood circulation. Here in the lymph node, cells of the adaptive immune system called T cells continually circulate between the blood and lymph nodes and are on constant alert for any sign that the body is under attack. Within the T cells, a small subpopulation called regulatory T cells control how the immune system will react to intruders. Dendritic cells
The flu virus uses its H spikes like a key to get inside your cells. N spikes allow copies of the virus to break away from your infected cells to infect more cells. There are 17 known types of H spikes and 9 types of N spikes that scientists use to name different flu viruses, such as the virus
Adoptive T-cell transfer, where T-cells are taken out of the patient's body, grown in the laboratory, and educated to recognize cancer or even modified to become much stronger. These fighter cells are then transferred back into the patient. A third enhancement approach is using stimulating factors called cytokines. Cytokines are stimulating proteins like interleukin 2, 7, 12, and 15 that cause the T cells to significantly multiply and get stronger. A fourth
virus has multiple parts. Inside the virus lies the genetic encoding that allows the virus to hijack human cells and turn them into virus factories. A protein encapsulates the genetic material known as the viral envelope. On the surface of the viron are S and HE proteins. The structure of the 2019 novel coronavirus is a mutation. For more information on this, see the link below. The large S glycoproteins are used by the virus to gain entry to human cells. They most likely attach to angiotensin-converting enzyme 2 receptors on the cell membrane, allowing the virus entry. The exact mechanism for this is not known. Most likely, as shown here,